One of the last concepts we'll talk about is the idea of polarization, which is going to be a fairly important topic, and you'll actually even do a lab on it. It turns out that if we take a look at our electromagnetic wave right here, that's electric field and magnetic field kind of propagating in some direction, the direction that the electric field points is going to be fairly important when we talk about polarization. Here we have it along the y-axis, however it could be at some angle to the y-axis, or at that angle, or that angle, or that angle. If we have light that has no preference towards which direction the electric field has, we would say we have light that is unpolarized. And so we'd say that the electric field could point in that direction, that direction, that direction, or that direction. You just don't know which direction it's pointing in, so it's actually all of them. If we run this light, this unpolarized light, through what's called a polarizing filter is going to have some axis with which it's going to polarize the light, or selectively transmit only light that has electric field lined up in a certain direction. So this polarizing filter is going to absorb all of the other components and transmit only the light where the electric field is pointing in the up-down direction. So we have light now that has some preferential polarization to it. You can kind of think of light as going through a picket fence, only maybe a very, very, very narrow picket fence. Now what happens if we pass light through two polarizers? We would also kind of call this maybe a polarizer and analyzer system, and I did actually use these when I worked at NASA. This is going to behave something with something called Malice's law, which is going to relate the intensity observed on the backside of the analyzer to the angle relative between this initial polarizer and this analyzer right here. So if we have initially some incident unpolarized light that's going to go through a polarizer, then the first thing that's going to do is that's going to preferentially lit only light with an electric field along this axis right here through it. That's going to essentially reduce the intensity by a factor of 1/2 of the initial intensity. So it's going to cut immediately the intensity down by a factor of 2. Now we only have light that's with electric field in this direction right here. However, we can also kind of break that into two components, that component right there and this component right here. Now we run this guy through an analyzer that's only going to lit light that's transmitted with electric field in the up-down direction right there through it. So it's only going to let this parallel component come through it. So the relative angle between the analyzer and the polarizer is going to determine how much intensity makes it through it. Now this cosine right here, you know that's going to go between 0 and 1. Imagine for a second this polarizer was not in that crooked direction right there, but suppose it was in this direction right here, so it's going to only lit the perpendicular component through it, and what would come through at this side would be nothing, or 0. So that's when the angle is 90 degrees. If this polarizer was just in the up-down direction, then it is going to cut the light down by a factor of 2 as unpolarized light goes through it. And then this analyzer right here is in the same direction as that, so the angle between them is going to be 0, and so it's going to just lit essentially I0 divided by 2 through it, which it's also calling I max. Now polarization can also happen in nature. It doesn't just happen in strange little polarizing filters. It turns out that when light is reflected, it is going to be polarized. So if we had some initially unpolarized light, say for example sunlight, and it reflects off of a nice perfect surface, then the light that's reflected is going to be polarized. And it's actually going to be perpendicular, or polarized perpendicular to the plane of incidence. So here we kind of have a plane that's in this direction right here. The light coming in was unpolarized, the light that's coming out is going to be polarized in that direction right there. This is a good example of why you want to buy polarized sunglasses if you're working around water. Water is going to polarize the light upon reflection, and if you were to put a set of polarizing sunglasses perpendicular to that, it's going to really cut down on the glare that you see coming off of water surfaces. Just a quick little note, we also could have something called circular polarization, In that case, the electric field is actually changing its direction over time. So at some time equals 0, the electric field might be up, down, and then at some later time right there, it's going to be in that direction. At some later time, it's going to be in that direction, and so on and so forth. So you can kind of imagine the electric field just kind of spiraling around as the light wave propagates. Scattering of light. Scattering of light is going to occur when the light has been absorbed by a molecule and then re-radiated, and it turns out that this is also going to polarize the light slightly. So if we had some light from the sun, as I said earlier, that light is initially unpolarized, it's going to be absorbed by air molecules and then scattered in different directions. Now the light that's scattered down to this person right there is polarized. You can take a set of polarizing sunglasses out and try this if you want. Something else is air is going to be much smaller than the wavelength of the sunlight, which is going to be roughly in the 550 nanometer range, and so the light that's going to be scattered is going to be preferentially blue. What this means is the person sitting on the beach is going to look up and see a blue sky. Someone way over here is going to be looking at the sunset, and it's going to see light where most of the blue has been scattered out, and so they're going to tend to see a red sunset. And of course, the age-old question, why are clouds white? Well, it turns out that cloud droplets are going to be much larger than the wavelength of light, so they're going to scatter all wavelengths very equally and very efficiently, and if we add all colors together, we're going to get the color white. And the last concept is that of Huygens principle, which is again a very, very important principle. Maybe not so much in this chapter, however, once we hit chapter 35 and 36, it's going to be kind of critical to be able to understand this. What it says is every point on a wavefront can be considered a source of secondary wavelets that spread out in all directions, and the speed's going to be the same. So what that's saying is we can take this point on a wavefront, and we're going to say that it is now the source, and it's going to send out a wave that's in all directions. This one's going to do the same thing, and this one's going to do the same thing, and so on and so forth. So what we're kind of seeing is we're seeing a secondary wavefront, but that secondary wavefront is not going to be a uniform thing. So we're going to have a crest, say right here, and we'll have another crest right here. But the reason why we have a crest right here is because all the secondary wavelets are going to add up along it. But we get that crest because we treat each and every single one of these points on the initial wavefront as a source for the secondary waves to come off of it. So let's take a look at Huygens principle and what it says about reflection and then refraction. If we consider a wave that has a wavefront that's in this direction right here, and so the rays are kind of pointing perpendicular to it, as it undergoes a reflection from this shiny surface, we're going to treat each and every single piece of this wavefront as a separate particle. At some later time b, we're going to say, well, we've treated each and every single one of these points from the initial wavefront as a separate particle. So these parts right here that are kind of imaginary under the ground, those have been reflected individually right here. At some later time c, we're going to have imaginary wavefronts right here where we've treated those separately, and they happen to add up along this new wavefront that we can see right here. So what this is kind of saying is that we want to treat wavefronts not as like a solid object, but more as like a linked chain. You can really see Huygens principle when we talk about the law of refraction here. If we have a wavefront right here and we treat each point kind of separately, then what's going to happen if we undergo if we go from material A to material B, where the index of refraction is going to be larger, and so the speed at B is going to be smaller than the speed of A, then what's going to happen is we're going to treat each one of these little points as a separate entity, and these wavefronts are going to slow down as they enter material B, but these wavefronts, they're still traveling at the speed of A. So you can really see quite well now that we can't treat this wavefront as a solid entity, but the linked chain metaphor seems to work quite well because we can have a kink in our chain. As the wave continues into the material, these wavefronts are going to slow down as well, and this one is going to continue at the speed of a, and then the wave is going to be entirely in the material, and it'll look like a solid wavefront again. However, we know that it's not. This also kind of can explain mirages. If you've ever seen on a hot highway, you can sometimes see what looks to be a wet spot. You could even see oncoming cars. In the desert, you might see something where it looks like this, where here we're an observer, and we're seeing kind of a strange little object that appears to be underneath the surface. What's going on is the hot air has a smaller index of refraction, and so light's going to be traveling faster. So we have our wavefront, which is the light coming off of the reflection of the camel here, and we treat each point as its own little entity. And so this part down here is going to go faster than this part right here, and the image is just going to bend back upwards towards the observer. It's going to look pretty wavy because it's going to be kind of non-uniform temperatures and everything like that.